Greetings, everyone. Welcome to the lecture on measures of variability. When we say measures of variability, we tend to mean how data may be able to vary within a particular set or distribution that is given. Measures of variability is a concept that helps us understand descriptions of the data, sometimes, for example, based on how much this data will be varying or how much it is different from what we calculate as the average value of a data. So, as you can see in the definition, differ from each other is known as the measures of variability. Now, when we talk about measures of variability, we usually talk about four main measures of variability: the range, the interquartile range, the standard deviation, and the variance. The range, as we know, is the difference between the highest and the lowest values in a data set. We will be understanding each of these topics one by one now. Second, interquartile range is the range of the middle half of a distribution. So when a data is plotted as a graph or plotted in histogram manner, the way the data will be falling, it can be concluded with percentiles as well. For example, we can find out the lowest 25% percentile, in the 50th percentile, or the middle value of a particular data set, as well as the higher 25% of the data, which is the 75th percentile. Now we try to find out in interquartile range the range of the data that is being or that is falling in the middle half of the distribution. Standard deviation and variance both are related in nature. However, they slightly mean different things. Variance is the average of squared distances from the mean. How much each score varies or how much each score is different from the mean is squared and summed up. That is the variance. And standard deviation is an attempt to standardize the variance score by calculating its square root. Now let's see how data can vary and why the variability measures are important to consider when it comes to data analysis. Let's consider these are the scores of a particular number of people in round 1 and round 2 of a particular test or a particular performance based evaluation. Okay, what we can see here, the first graph scores ranges from 4 to 10. Even in the second graph, scores ranges from 4 to 10. Now, based on the way scores are ranging, if we try to find out the or calculate the mean of these both this distribution, the mean will be same. However, you can see the way the data is distributed. No, over here it is more closely distributed, right? It is not varying too much from each other. However, in the second round, we can see the data is spreading in a larger context or to a larger extent, indicating that there is more variance or difference between the there is less difference between the way people have scored. For example, here, um, two people have scored, let's say, a score of 5. However, around 6, around 6 people have scored the mark 6. 5 people have scored 7. 8 people have scored 4, right? So when you see how much people are scoring in terms of how much the scorers of 5 pointers are different from the scorers of 6 pointers, we can see that they differ a lot. However, in this distribution, because of the spread and because of the way the data is spread, we can see that they will have lesser variance from there is a possibility that they have each score in the data varies lesser from the mean. So even though the mean of these two distributions are same, The variance is different. The way they are distributed is different. How much data is sitting away from the mean will be calculated, and we will find that both this distribution, apart from having the same mean, will have different variance. The first measure of variability is the range, which is usually calculated by subtracting the lowest score in a distribution with the highest score. For an example, here's a data set with 10 numbers. They are not yet arranged in ascending or descending pattern. However, if we arrange it, or even without arranging it because it's just a small number of data, we can see that 99 is the highest score in this data set and 23 is the lowest score in this data set. The range for this data set will be the highest score, which is 99, minus lowest score, which is 23. And the resultant number that we get is the range of that particular data set. Next topic is inter-quartile range. For inter-quartile range, we depend on the calculation of percentiles, and the inter-quartile range is the range of the middle 50% of the scores in a distribution. It can be computed as the 75th percentile, or P75, or Q3, minus the 25th percentile score, or the Q1. Okay? Now, when we do P75 minus P25, we are left with the middle 50% scores, or the 50th percentile range scores. One related topic to interquartile range is the semi-interquartile range, which is the interquartile range divided by 2. Once we get the middle 50% of a particular distribution of scores, we can divide it further into two more equal halves, which is dividing it by 2, and that gives us the semi-interquartile range. The importance of understanding these topics is that the median score of a particular distribution plus or minus the semi-interquartile range contains half of the scores in a distribution when we are talking about a symmetric distribution. Okay? However, the outcome of the same will be different when it is a distribution which is not symmetric. So, to get an idea about the spread of the data, we can also use that the semi-interquartile range, median and semi-interquartile range, to find out if the scores in the distribution can actually attain a symmetric distribution, which is 50% on either side of the middle point, which is the mean, median, and mode point of the particular distribution. Next, we have the variance. The variance is, as we have already talked about it, is defined as the average squared difference of the scores from the mean. Each score in a particular data set will differ to some extent from the mean, or majority of scores will differ to some extent from the mean. This difference is calculated from each score by subtracting the mean from each score, and then finally they are summated, or the summation of the same is used, and it is divided by n, or the number of frequencies, or the number of occurrences. Now this formula applies for when we want to calculate the population variance, where we have the population's frequency and the population's mean, the entire population's mean. Now in this formula, the sigma square is indicating the variance, mu is the mean for the population, and capital N is the number of numbers, or the number of data that we have. The mean deviation from the mean is usually 0. That is why we square the item so that we do not achieve something called the 0. If the variance is of a sample, then to estimate it, we use the formula as follows: S square, or variance, equal to summation of, again, score minus mean. The expression of the term mean has changed here because it is about sample mean, whole square divided by n minus 1. Now everything else is similar in this formula except for the term n minus 1. We use n minus 1 to adjust any particular presence of error that might be there, because we are deriving the variance now from a sample only for the entire population. The reason being here is, let's say When I'm taking data from a population in terms of a sample, that population has the potentiality of giving us multiple samples. Okay, if our research is on a population, on a particular population whose known number, whose recorded number is, let's say, 1000, it is possible for us to draw around 10 to 20 samples from there. Each sample can have 30 data, 40 data, okay, 100 data, etc. So, based on this, if we calculate the mean for any one of the sample, we get the mean score, or we believe to get a mean score that might be identical to the population mean. However, to test it further, if we draw further samples from that particular population, we for the same study we or to apply the same test, we draw multiple samples from that particular population of 1000. Okay, then each of the sample population grouped as sample population 1, sample population 2, will also have their own mean, which might not be identical to each other. They might not be the same score. This is an indication that there is a possibility that we are not assuming the population mean accurately when we are taking a particular sample. To make adjustments there so that we try to attain a mean that is as much as possible close to the mean of the population, we use the notion n minus 1, which also means degrees of freedom. Degrees of freedom means the extent to which uh, particular numbers of data in a data set have the freedom to vary. Okay? If we say, in a data set we have numbers 1, 2, 3, 4, 5, okay, and the total of this data set, for example, is 1, 2, 3, 1 plus 2 plus 3 plus 4 plus 5, which is 9, 10, 11, 12, 13, 14, 15. Let's say the total is 15. Now, keeping the total as 15 only, these numbers 1, 2, 3, 4, 5, many of them have the eligibility to vary independently. For example, the data score 1 can be 2, 2 can be 1, okay, 3 can be 4, 4 can be 3, right? But however, after all these variance is happening, one digit will be left which will not have independence to vary on its own wish. It will have to obey to vary as is required to add to the total of 15. Okay, for an example. So, in this data set, every other value has the liberty to vary to different extents, except for one score, which will have to mandatorily vary only in such a way that we achieve the total 15, right? So that is why degrees of freedom is everyone else in the data set except for that one data, hence n minus 1. Okay, this is a as much as possible, I'm trying to give a very uh, simple example of what is degrees of freedom. Simply, in a population, when we are drawing a sample and a mean, or there is a possibility of drawing multiple samples, there is also the possibility that some of this data has the independence to vary, except for the last one data, which has to obey with the only left out criteria that they can take up to fulfill the ultimate score that we can calculate for the population. So degrees of freedom usually is calculated as n minus 1, and we are using here n minus 1 to make an adjustment to avoid any kind of error that we might encounter in assuming the sample mean to be similar to the population mean. Variance calculation of variance for grouped data will include us finding values of every score minus the mean score, and putting and multiplying the square product of it by the frequency, by the summation of the frequency divided by the summation of the frequency. We'll get a better look into it using this data set This is a practice data set. So let's say these are your class intervals, okay, and these are the frequencies. Now in grouped data, we usually take the mid value as a representative of the scores that are lying in this class interval. Likewise, we're going to take the mid values for all these class intervals, which will help us get an idea, or which will help us assume that yes, these mid scores are acting as central tendency median for all these class intervals, and it is representing the scores that might be present within these class intervals. If 10 to 25 has two scores, then 17.5 is representing something closer to the two scores that is there. However, we will also have to calculate, or it is not required here, but it is required when we are calculating the mean, okay, to multiply the um, mid value with the frequency, because there are two scores here. If 17.5 is representing the two scores here, then there has to be in an assumption, or to the most approximate assumption, to 17.5. Okay, so calculation of the mean will require us to calculate the frequency multiplied by the score. Once we multiply that, we get this final row of scores. Okay, and to find out the mean, we add them up. We find out the summation of fx divided by total number of n, which is the total number of frequencies. In this case, it is 30. So 1860, which is the summation of fx divided by 30, is 62. So our mean is 62. Once we get the mean, it is easier for us to put the values in the variance formula. We go one step ahead and we calculate the summation of f x minus mean whole square. We calculate this. Okay. Please ignore the non-presence of, or the way the formula is presented here. This, I would say, it is the calculation of this particular part of the formula. Okay, f into x minus mean whole square. So in each of these scores, our frequency for the first row is 2. Okay, we are taking the mid interval value as the score. So 17.5 minus what was the mean? 62 and square. This we repeat for each of the mid values of the class intervals. And finally, these are the values you are getting, which we are terming as summation f x minus x bar, or mean whole square. The summated value is 15,067.5. Applying these values that we have in the formula, variance is 15,067.5 divided by n, which is 30 in terms of population. Okay, if this is a population data, it is n, which is 30. Had it been a sample data, it will be 30 minus 1. So we get the mean as, we get the variance as 502.25. Okay. Now, going back to another concept called the standard deviation, which, as I already mentioned, is the standardized version of the variance. And how do we do that? We square root the variance. So it is the most easy way to understand standard deviation is to understand that it is the square root of the variance. Standard deviation calculates the spread of the data from the mean. Variance calculates how much each data is varying from the mean, and standard deviation calculates and standardizes how far, or how in what and how much of deviation we have to plot the data in a particular distance from the mean. To do that, we use z-scores to express standard deviation, and standard deviation z-scores are usually taken from ranges of 0 to plus minus 3 standard deviations, where the positive side, the right hand side, will have the positive standard deviations and the left hand side will have the negative standard deviations. Data as much as they are closer to 0, which is supposed to be the midpoint in a particular normal distribution, are majority usually in numbers, and it keeps on decreasing as it moves towards a standard deviation of plus minus 3 on either sides of the mean in a particular normal distribution. The formula for standard deviation again, as we said, it is the square root of variance. So the variance formula stays, we just add a square root to it. And here we only state the standard deviation as sigma, not sigma square, because standard deviation is not supposed to be a squared value. Variance is, so we say sigma square for variance. For sample population again, the same variance formula stays, right? We only add the square root symbol to it so that we get a square root value. For group data again, the same variance formula stays, but we take a square rooted version of it. So let's say if we have found our variance using this particular part of the formula, okay, in the current example that is going on, if we have calculated the variance using this particular part of formula, then we have also calculated the standard deviation at the same time. However, the final variance value, what we are doing is we're putting the root over here at the end, and we are getting the standard deviation here. Okay, so what we used here is the population variance standard variance formula, and we got this as the population variance, and the root of it we're getting the standard deviation, population standard deviation. Okay. That's all for the concepts of measures of variability. I hope this lecture will help you. Thank you so much for being patient and listening.